So I guess should we start?
Yes, we can. Right.
Okay. Yeah. So thank you very much, everybody, for joining. We have 32 participants from around the world. We have many people from NTNU, from our bachelor programs in computer science and the bachelor programs in automation. We have also many students from our master program in simulation and visualization, and it's the only international program of its type in Scandinavia in simulation and visualization. We really wish to have maybe later on a webinar about research activities at simulation and visualization. We are a department of ICT and natural science. We are part from IA faculty at NTNU. We are located in a very nice city and a beautiful city called Ålesund. Our faculty consists of 5 departments. We are one of those departments in Ålesund. There is also another department in a city called Gjøvik, close to Oslo, and 3 other departments located in Trondheim, the main quarter of NTNU. We offer 2 bachelor programs in computer science and automation and robotics, and also we offer an international master program in simulation and visualization, which is international. And one of our goals is try to attract more national and international students to our international study program. It's exciting because we are working in simulation and visualization. We have lots of research activities in different application areas, in machine learning, in medicine, in smart city, which is really very important, intelligent transportation systems, and so on. We have very nice courses in visualization as well, visual computing. And today we are really very happy to have Professor Anis from Princess Sultan University in Saudi Arabia. It's very exciting to have him and to give us a talk today about robot operating system. And many of you knows already Professor Anis. He has very well and very strong research profile. Professor Anis, he is professor in computer science, and he is advisor to the rector and leader of robotics and Internet of Things research lab in Princess Sultan University. He is also R&D consultant at different several companies in China and in Portugal. He has been the chair of ACM chapter in Saudi Arabia since 2014. He is also a senior fellow of Higher Education Academy in UK. He received several awards, including Rector Research Award in 2010 at Imam Mohammed bin Saud University, and the Rector Teaching Award in 2016 at Princess Sultan University. He is a very famous figure in area of robot operating system, and really we are excited to listen to him today. Today will be part 1, and after 1 week we will have another part 2. Today it's robot operating system, how did it revolutionize robotic software development, part 1. It will be in 24th of April, and next time Prof. Anis, it will be 4th of May, I guess. So part 2
yes,
will be
after 2 weeks.
After 2 weeks. So we will have after 2 weeks part 2, and during those 2 weeks you need to start working with ROS. Implement it in your computer, for example, try to practice exercise. And if you have more questions, we will have those questions after 2 weeks. But today also we will have some questions by the end of this webinar. It will take around 45 minutes, and after that you will have a chance to give some questions to Professor Anis. So the stage is yours, Professor Anis, and thank you very much for joining us today.
Okay, thank you very much for the introduction. I'm going now to switch to my screen. If you can allow me to share my screen.
Yeah.
Okay. Okay, 1 moment. Are you seeing my screen? Are you hearing my voice well?
Yeah, very well.
Okay. بسم الله الرحمن الرحيم والصلاة والسلام على نبينا محمد وعلى آله وصحبه أجمعين. Thank you very much, Dr. Ibrahim, for your invitation and for the introduction. I am very glad and delighted to provide presentation on robot operating system. This is something that I really love to do. I working with ROS, teaching with ROS, or learning even about ROS. This is something very exciting. So I'm going to take you through my let's say, my experience on how did I start with ROS and how I did use it for education and research. And I will try to emphasize how robot operating system was actually revolutionary in terms of the robotic software development. At least from my perspective as a computer scientist working in robotics, I mean, it's not maybe something very common because usually in the robotics area you can find people from mechanical engineering, electrical engineering, or computer engineering. But usually computer scientists try to do something at the algorithmic level or algorithm design, stuff like this. But I actually went into the experience into going to the robotics from the computer science perspective. And I would say that one of the reasons of going there is because of robot operating system allows me to really make a lot of abstraction in what concerns robotic hardware and low-level drivers and so on. So I'm going just to give you an overview about robot operating system version 1 and version 2, ROS 2 also. And also we'll give you some information about the different activities that we have been running around ROS. So first of all, let me introduce my research lab. So 2 or 3 years ago, we were like kind of very small team with just one office with 2-3 researchers working on different areas of robots. This is some students that I have been teaching the robotics course back in 2016. We were doing some kind of hands-on activities on drones and assembly, stuff like this. And later on, alhamdulillah, we have expanded a little bit more. And now we have a larger research lab with a lot of students being involved. We perform training for students, for government sector, for industrial sector, and we work on different areas. We're not only confined to the robotics or Internet of Things, we work very heavily on deep learning, artificial intelligence related issues, computer vision, and trying also to provide solutions for the industry. This is one of the trainings that we have been doing for STC Specialized, the biggest telecommunication company, for their engineers about 2 drones programs that we have established, one for the assembly of the drones, and the second one is about photogrammetry and aerial surveying. Yes, so this is basically an overview about the things that we have been doing so far. So the robotic lab now also accepts students from all over the world. We have visiting PhD students program. So we have PhDs, we can invite PhD students to come to join the lab for a period starting from 1 month to up to 6 months. That is renewable also. And we have postdoc program. We have recruited different postdocs, research assistants. We have full-time researchers as senior researchers or postdocs. We have also research professors working on in our lab. Okay, let me give you an overview about the latest project that we have been developing in the context of the activities of the Robotics and Internet of Things Lab. So basically, we have projects around artificial intelligence. For example, here we work on smart transportation systems from aerial images captured from drones. And in this system, we are able to estimate the average speeds of vehicles. We are able even to locate if there are some accidents or there is some low infraction. This is another program that we have developed for the pilgrim detection and monitoring in Hajj areas. This is to estimate also the number of people in the crowd using some artificial intelligence technique. And this is another application using also deep learning about the drifting detection, because this is a common problem in Saudi Arabia. You can find some youngster that drive like in a crazy way the car, so we try to provide solutions about how we can detect them automatically from surveillance system. We have some solutions also for street fighting. All of this using artificial intelligence. This is another program about prayer monitoring also for kids. And we have some works around face recognition. This is one application that we have developed for lab access using the face recognition. And a couple of other things. This is for searching people in the crowd based on some criteria. And we have also worked on aerial images for palm counting, for also car detection. We have some solutions related to monitoring palms through the Internet of Things and the detection of the red palm beetle insect, which is a major problem in agriculture because it actually destroys a lot of palms. And several other things. This is one of the things that I'm going to present later. It's a demonstration that we did for Huawei in the inauguration of the 5G Networks Lab of STC, the teleoperation of a robot using 5G networks and ROS. This is like one of our ultimate solutions on how we can control robots over the internet with video streaming as well. We have also some different types of drone projects, like photogrammetry projects, 3D reconstruction, site surveys, and we have also a group of racing drone students. And these are also the training that we conduct for the government or for the industrial sector. So this was just an overview about the different projects that we have been working on. Okay, so let me give a brief overview about myself because this is actually pretty much related to why I have been working with ROS. So basically back in 2009 or 2010, I was just like basic computer scientist working on areas related to wireless sensor networks and quality of service, networking issues, and so on. And I decided to do some project around robotics, but I wanted to do them from the computer science perspective. Things related to multi-robot coordination, so we wanted to design some algorithms for the collaboration between robots and also try to investigate some possible path planning algorithms on how to design some path planners and so on. So being actually a practitioner, I wanted to implement these techniques into robots. And at the same time, I like developing high-level softwares for the applications that I'm targeting, but I don't like actually to program at the low-level drivers, like, for example, developing the hardware or making C drivers for different type of hardware and so on. This is something that we don't like to do as a computer scientist. And it's really enjoyable to work with robots, but there are a lot of complexity in what comes to, for example, the kinematics of the robot, the dynamic models, and everything that from mechanical perspective or electrical engineering perspective. So in the beginning, we were able to implement this algorithm, but it was kind of very basic because we did this at like in a simplistic manner, considering that we didn't have a comprehensive framework like robot operating system. So I'm going to show you how did we start working with robot and how ROS actually have changed all our way on developing software for robots. And probably this is related to my experience, but I think it can be actually generalized to why ROS is really a very important framework for developing robotic software. So during this lecture, I'm going to provide some intuition why ROS is important. I will provide an overview about ROS and ROS2, and then I will talk about the contributions that we have done around ROS, both in terms of education and research. So why robot operating system? Let's consider this is one of the projects that we have been doing back in 2010. We were working on path planning algorithms. And this is a nice platform, the Wi-Fi bot robot, but at that time it didn't support ROS. And at that time ROS is still starting. I mean, maybe it's still version 1 or version 2. It was not that popular as it is today. So we had to implement everything. In this simple application, we just need to hard code everything, the location of the robot, the path that it has to follow. It was kind of manually hard coded. We don't have any kind of sophisticated way to build a map or so on. So this was one of the first prototypes where we tried to implement some kind of path planning algorithm, but at a very simple level. And okay, also in terms of the reactive navigation of the robot. So same thing here, if you want to avoid obstacles without hitting obstacles, so you need to use like sensors like ultrasonic sensors or laser sensors. But if you do this, if you do this manually, it's really a painful way. Usually you have some kind of low-level C API that is very limited. So I remember then when we wanted to make this robot move, we have to send a low-level command to the right, to the motor in the right side and to the motor into the left side. So you need to send the signal. If you want to rotate, you need to send a signal that is higher in the right side as compared to the left side. If you want to move forward, the signal has to be the same. It was kind of really not that easy to develop robotic application because you have to deal with very low-level APIs at the C language level. Also, I remember another project, we wanted to do some kind of collaboration between drones and robots, so we wanted to make a drone fly. And I remember we have taken this Aztec Firefly drone, which is very sophisticated. But programming it was really kind of nightmare. Without using ROS, it has a C++ API that was not really trivial to work with. At least, as I mentioned to you, we have computer science profile, and we would like only to consider on developing at the high level. Okay, we don't want to go into the deeper level, going into the drivers or how. We want something like make things easy. I want the robot to take off. I want just to send take off command. I want the robot to move forward. I need to send just a forward command or some kind of velocity and so on. But these kind of things were not easy in the low-level APIs that were provided by this different robotic platform. So we found out that there is kind of limitation if we want to bring our models into reality and implement them into robots. Until in 2011, I think I remember maybe I have heard about ROS in 2011, and when I started to dig about it, I found that it provides really the things that we really need to move forward in terms of the implementation of our algorithm. So now if we make abstraction to any robotic system, we can consider that the robotic system basically, it performs three actions. It senses, okay, this is what is related to perception. It then processes the information that it receives from its sensors. Okay, this is let's say the thinking part. And finally, it will make some kind of actuation, maybe moving from one location to another, or moving the actuators of a robotic arm, or if it is a drone, it's going to fly, and so on. So what ROS actually provides to you, it provides very nice abstraction to the perception, it provides very nice abstraction to the low-level drivers and hardware. So you don't need to know about which hardware you are going to work with, because ROS is going to provide some kind of interfaces that will allow you to easily manipulate any kind of sensors and any kind of actuator. Now, for example, if you want to use a camera with ROS, you don't need to know, okay, which camera brand I'm going to use, how should I bring the signal from the camera, or how should I capture the image from the camera. Or if you have a laser scanner, you don't need to worry about this. All you need to do is just to know how you can bring this information from ROS. So usually ROS provides all the interfaces and provide all the low-level software APIs to extract information from the hardware. And then as a software developer, you just need to focus only on the information that you can take from ROS, which we call ROS topics, for example, or the information that is flowing around through the ROS messages. Same thing for actuation. If you want to make the robot move, you just need to publish some kind of message. And the good thing in ROS that it provides some kind of standard APIs. Okay, if you want to make the robot move, you have like the twist message that allow you to send twist commands either to a robotic arm, or you send twist command to a ground robot, or you send twist command to a flying robot, or anything else. So as a software developer, all what you are going to focus on is the thinking part, is the processing part of the information. How are you going to transform the data coming from the perception modules, okay, into the actuation modules? So you can focus on this, and this is what I actually wanted to have. I didn't want to bother myself about how to collect data from the sensors or how to send information to the actuators, but we want to focus on the high-level APIs. This is just one perspective of the benefits that you can use of using ROS. Of course, there should be so many others. But it really makes a lot of simplification to the process of the software development. Now, imagine that you would like to develop a self-driving car. Okay, this is something possible. We have already real products about self-driving cars, and basically they also use ROS. But for this, you will need several modules. You need a perception module, okay? How to collect information from different cameras, how to collect information from laser scanners, from LiDAR sensors, okay? You need also to process this information, okay? You need also different libraries and framework, for example, for computer vision or for matrix computation, or you need some kind of predefined mathematical models. You need also a way to communicate between the different sensor and hardware. You need also some artificial intelligence and machine learning strategies in order to be able to process the information and transform them into appropriate action. So if you don't have ROS, you have to bring up all these different tools together. But the great benefit of ROS that it provides you a standard way. It provides you one ecosystem, a unified ecosystem, a standard ecosystem with all the functionalities that you need to develop your software. So it will eliminate all the hurdle and the headache of trying to find out what kind of tools and software you have to use. And if you work with open source, everybody knows the problems of compatibility issues, the different issues of versions and stuff like this. So ROS makes everything compact, bringing them into one ecosystem and provide reusable components that can be easily integrated in any kind of application. Okay, so this clearly shows the great impact and the benefit that ROS bring to the software development of robotic platforms. Without this, it's going to be pretty much difficult. I mean, in the area prior to ROS, most of the software developers of robots, everyone would have its own proprietary software, and there is no compatibility. So if you want to make one robot work with another, it's going to be very difficult because they use different software abstraction, they use different software APIs, and they use even different type of communication protocols. Now everything with ROS becomes unified and standardized. So we can consider ROS as the de facto standard for the robotics software development. Now, seeing the impact of ROS, this is one snapshot taken from the metrics report of Open Robotics in July 2019. So you can see the statistics over the month of July. It's a huge number of users all over the world with a big concentration in China, in the United States, Japan, Germany, South Korea. And basically, there are 2 million page views per month in the month of July 2019, and up to more than 120,000 new users every month coming into the ROS world. So this actually shows the significant impact into the robotics scientific community. I mean, now everyone who would like to learn about robotics, the first thing maybe he need to start learning is how to develop software with ROS. You can see also the increase of the number of users. Now here also this is taken from the metrics.ros.org. You can find it over there. And you can see here the blue line, the increase of the number of users every year. From 2011, basically the start of ROS. Basically I've started to use ROS from this year until 2020. And you can see here there are some kind of few jumps. I guess that this is during the ROSCON period. I mean, ROSCON period is around end of October every year. So what is ROS now? ROS, basically, we can consider ROS as a middleware, okay? As a middleware that provides high-level abstraction between low-level hardware and drivers and high-level software APIs. So in this slide, I show the different distributions of ROS from maybe when it was a small project in 2007, from Willow Garage and Stanford University AI Lab. And then, let's say the first release was in March 2010 with the box version. So usually with ROS we have different versions, and every time we use the letter B, the letter C, the letter D as first letter to design the name of the version. Okay, I have been using ROS from the electric version, and now we have the latest version that what was released for ROS 1 is the melodic version, released in 2018. And basically, some of the versions, they have long-term support. So that's why they are more popular than others. I'm going to show you now which versions have been pretty much used over the time in the following slides. So you can see here the evolution of usage of the different ROS versions. So for example, you can see from 2014, okay, we have the ROS Indigo version. This is the long-time support. Is it possible to mute the, there is a background noise? Yeah, okay. So you can see ROS Indigo, this is one of the long-time support version. It has taken, this is in the blue color here. It has been very active until around 2018. And then there is the ROS Kinetic, that is another LTS version. So you can see, for example, for Jade, it's not a long-time support, a lunar long-time support. It's not pretty popular among the ROS users. ROS users basically would like to use the long-time support versions like the Kinetic. Kinetic is still being actively used until now, although it was released in 2016, but still it's being used around by 50% of the ROS users. And also we have melodic that starts also to take some, to have some impact in the last couple of, in the last 2 years, 2019 and 2020. So now comparing the usage of ROS and ROS 2, you can see even now until March 2020, most of the people are still using ROS 1 version, despite that ROS 2 version was already released in 2017 the first time. With the Ardent version, okay, here. The issue is that ROS 2 is still under development, and I think the future is going to be for ROS 2 because it is addressing a lot of issues and a lot of problems that ROS 1 users have faced, and I'm going to explain the difference between both versions. But still, until now, most of the users are focusing on ROS 1, only very little. Okay, so the last version of ROS 2 is Eloquent and is going to be released in next May 2020. The current version is Dashing now, currently available. Okay. So let's look at the ROS architecture. Basically, ROS, it is composed of the concept of nodes. And nodes, basically, they are processes running into a computer. Okay, so you can define one program here, you can call it a node, another program, it's called a node. And these nodes are going to register themselves using the ROS master. The ROS master, this is the core node of a ROS ecosystem. Now, in ROS 1, in order to be able to run ROS, first of all, you need to run the ROS master node. And finally, all these nodes will be able to communicate with each other after registering themselves into the ROS master node. And of course, this makes one of the problems that it is prone to the single point of failure, because if the ROS master is crashing, so your total application, all the other nodes will be crashing as well. And then ROS defines different client libraries, both in the Python programming language and in C++ programming language. So these are the two main programming languages. Also, there are some client library in Java, but they are less popular. And it uses TCP and UDP for inter-process communication. And basically, ROS 1 was developed for Linux operating system, although there are some like experimental version for Mac and Windows, but they are not of pretty much use in what concerns ROS1. So this is the the architecture of ROS. And now let's introduce the main concept of ROS. Usually when you want to start a ROS application, first of all, you need to start the ROS core, which is the ROS master. And then you can start different nodes. Now, for example, we are going to start one node that is our robot here. And another node here for the teleoperation. So the first thing, these nodes are going to contact the ROS master to advertise themselves. So this one is going to say, okay, I am a robot. I'm called Turtle Sim. I'm subscriber to velocity message. So if there is any velocity message, you can send on the following topic over the following message. And same thing for this teleoperation node is going to advertise itself, giving its name. It's a publisher of velocity command, okay? And this is the type of message. And then this ROS core is going to make the connection between these two different nodes. So finally, these two different nodes will be able to communicate directly either using TCP or UDP. So this is the whole life cycle of how to run a ROS, let's say a ROS program here. Let me show you a demonstration. Maybe we have some people that are new to ROS. Okay, so basically the first thing you need to do is to run a ROS core. This is the ROS master. Without running the ROS master, you cannot run any application. And then you can write your different nodes. So a node simply is a program. It's a process that will be running. Now this is the process running the robot. And here we have a simple Turtle Sim. This is the best tool to start learning about ROS. Very simple and makes a lot of abstraction, but the same way can be applied to any real robot. And then you open the teleop here. So this is another node that is the teleop, from where you can send commands to make this robot move. Okay? And now, if you want to check the number of the list of different programs that are running into a ROS ecosystem, you can use some very simple terminal commands like ROS node list over here. Okay, sorry. Okay, so ROS node list is going to give you the number of the different processes that are running currently into the ROS ecosystem. You can check what are the different topics through which you can send messages. Now, for example, you want to send a velocity message, so you know that the velocity message is defined by the following topic name. And finally, you can also monitor the messages running through a topic. Now, if we make the robot move, you can see that we can see the messages that are running. And this is also a very simple example on Turtle Sim, but the same process can be applied on any kind of robot. And this is actually the universality of using ROS, is that you can use it with any kind of robot in the same way. The same way that you use Turtle Sim, you can use it for any kind of robot, whatever it is, a robotic arm, or if it is a drone, UAV, or anything else. And finally, you have different programming APIs, like for example, you can define a Python program or C++ program to run your node. Of course, here Python is pretty much simple, much simpler than the C++. But of course, C++ might provide better performance if you need some kind of real-time execution performance. Now, in terms of the, let's say, communication paradigm in the ROS operating system, we have three main communication approaches. We have the publisher-subscriber, which is the most common. So basically, you have some nodes that will work as publisher and some other nodes that will work as subscriber. Okay, so let's imagine that you have a laser scanner like this, and you have a node that would like to avoid obstacles. So what you will do, you will just subscribe to the information coming from the laser scanner. And the laser scanner is going to provide you all the information about the obstacles that you have. It's going to provide you an array of distances and these distances will provide you what is the obstacle in every orientation. Okay, so the subscriber can use this information and develop algorithm to avoid obstacles. Okay, and this can be applied with any other kind of device. Instead of having a laser scanner, you can have a camera, for example, or you can have any other kind of sensor, ultrasonic sensor, or any other kind of sensor. And the publisher, okay, so imagine that now you know all your different obstacles. In this case, you can publish a command that is the velocity command to tell the robot to move to a certain location and to avoid the obstacles. So basically, the publisher and subscriber, this is the most common model, communication model between the different nodes into ROS ecosystem. You have also ROS services, and here you will have a synchronous communication between a client and the server. So one server is going to provide some services, and the client will need to communicate to send a request and receive a response back. So this is different from the publisher subscriber, because here it's one-way communication. It goes always from the publisher to the subscriber. Anything that you have new, you are going to send the new information to the subscriber without having an explicit request. Otherwise, in the services, the client is going to send a request, receive a response, and then the communication is going to end. If you want to have another information, you have to send another request, and then you will get back another response. So this communication paradigm is synchronous. Okay? So the client, when it sends a request, is going to wait until the response. So it's going to be blocked until the response is coming. So ROS community has found another way of communication that is called the ActionLib. And ActionLib is completely asynchronous. It's like you have also a client and a server, and the difference here is that the client will send a request, and then it can do anything else. It will not be blocked until the response is coming, because sometimes the response is going to take time. Okay, and whenever there are some intermediate states, so the server is going to inform the client, okay, I just achieved, for example, maybe 20% of the work, 30% of the work, or 90% of the work. And finally, when the work is completed, the server is going to say, okay, the work is completely done. An example of ActionLib is the move base, that is the navigation stack of ROS. So basically, in the navigation stack, you send the client, any node in your ecosystem will send a goal location. It will send a goal location to the move base server. So during this time, the move base server is going to execute the local path planner and the global path planner to make the robot move. And in the meanwhile, the client can do other things, for example, making other computation or getting some sensor information and so on. In the meanwhile, the move base is going to send to update the client with the state of the mission, what is the current location of the robot after moving, and finally, when it reaches the location, the target location, it is going to say, okay, the mission is completed, or maybe if the destination is not reachable, it will say unable to reach the destination. So move base, basically, this is a popular example of using ActionLib in ROS. So these are the three main communication paradigm: publisher, subscriber, ROS services, and ActionLib. Another very important thing in ROS is that it dramatically simplifies the navigation. I mean, navigation is very, very complex. You need to build a map. You need to navigate inside the map. You need to be able to specify the locations where you want to move. You need to avoid obstacles. This is one of the most difficult operations that someone has to do with a robot. And fortunately, ROS provide all the needed abstractions and APIs for easily navigating inside any environment. It provides some packages for building the map using SLAM, and provides some other packages for making the navigation using a robot. And basically, the works that are implemented, they are dated from 2000, from the thesis of Sebastian Thurn about probabilistic robotics. It's very nice work from 2000. Also, some other works related to the local path planner, the DWA algorithm. And now all these different techniques are implemented into ROS and comes working out of the box with just need for small configurations only. Okay, so something to know is that ROS provides two types of path planners. We have the global path planner, which is responsible for providing the path from the initial location to the target location. So it's going to make a path planning algorithm like, for example, A** or Dijkstra. And you have the local path planner that is responsible of executing the path that is found by the global path planner. Okay, we have released a book that is called Robot Path Planning and Cooperation, in which we have developed different path planning techniques, and we have also demonstrated how we can implement the new path planners as a global path planner into ROS. So I consider that the navigation stack and the TF package is one of the most popular packages in robot operating system that makes it really easy for anyone to develop navigation algorithms for mobile robots. Okay, so far I have presented the benefits of the robot operating system, but still it has some limitations. So the limitations of ROS, that it is basically designed for the single robot case. It was not designed for the swarm or the communication of robots. That's why if you want to do multi-robot cooperation with ROS, either you need to develop your own packages for multi-robot communication, or there are some contributed packages that are provided by some researchers. But there is nothing native that will allow the robots to communicate between each other using robot operating system. Another issue with ROS is that it is not real-time. It is based on UDP and TCP, so from processes perspective, all the processes would have the same priority, and maybe we need to differentiate between the priority we need to differentiate between the priority of the processes running into a robot, because sometimes you may have processes that have higher priority. For example, if you have a process to avoid obstacle, this is more important than, for example, another process for example, moving a robot or something else. But in ROS, there is no way to say that this process or this node has higher priority than the other. Another thing is that ROS requires a very reliable network, because basically ROS will be composed of several nodes, maybe tens of nodes, and all these nodes will communicate between each other, and every node is going to consume a bandwidth. So you will assume that you have a high and reliable bandwidth connection, network connection between the different processes running inside the robot. And this is something maybe not easy to provide every time. And another thing is the problem of ROS master. And we have the problem of the single point of failure. So that's why the ROS community, I think maybe in 2013, 2014, they started to think about another alternative of the current ROS operating system, and they started to design ROS 2, okay? And the idea of ROS 2 here is, first of all, to get rid of the ROS master and to change it with a more standard way of the communication between processes. So the processes will be standalone. They don't have to be registered with a central node that is the ROS core or the ROS master. And for this, they have used the standard data distribution DDS here for the communication between the different nodes. And different changes were done for the client libraries. So still we have the Python client API and the C++ client API. And hello? Okay, other changes is that ROS 2 was not only designed to the Linux operating system, but also it was designed to be cross-platform for Linux, Windows, and Mac OS. So several of the limitations of ROS were addressed in the design of ROS 2, which is currently being developed by the ROS 2 community. Okay, so ROS 2 actually target to use a swarm of robots instead of the single robot case. It also implements quality of service and real-time guarantees. So there are ways to define quality of service profiles between the processes, so you can give a priority to one process over the other. It is also designed to be a cross-platform, and the objective is to facilitate the transition from prototyping to production. Now, when it comes to designing what kind of middleware, so in ROS 1, basically it has its own proper middleware that is based on ROS TCP and ROS UDP. So one alternative was try to improve the legacy protocols, okay, to make them real-time and so on. But at the end, the second strategy was to build a new or to use an existing solution, like for example, 0MQ or protocol buffers from Google, 0conf or DDS from RTI. So finally, DDS was actually selected to be the middleware. Instead of using TCP ROS or UDP ROS, DDS is going to replace it for the communication between the processes, and this is going to give much more scalability and flexibility, real-time performance, quality of service, and so on. So what is DDS? Is the data distribution service. It's already an industry standard communication system, okay? It's an old system. It's independent from ROS, but it was later on integrated into ROS, and I'm going to explain the why. And it is designed by the Object Management Group. It is a data-centric publish-subscribe system, so it basically shares some common features with ROS in the sense that it provides publisher and subscribe mechanisms. It provides real-time machine-to-machine communication, and it is used in different application contexts, like the financial trading, the air traffic control, smart grid management, big data, and IoT applications. Yeah, and it's pretty much all started in 2001 by RTI in the US and Thales Group in France. So why DDS? This is a presentation that I have found on YouTube from Rick Warren, okay, from RTI, which is the main developer of data distribution system. And looking at how DDS work, or the concept and terminologies, so let's look at the different concepts. In DDS, they define the kind of domain. Okay, so the domain, this is like we differentiate between different domains or different subsystems and or of a particular application. Now, for example, in our case, the domain is going to be ROS. And they define similar concept to ROS like the topic. And the topic here is a group of similar things. And below topics in the hierarchy, you have instance. And it's defined as individual changing things. And besides the instance, you have a sample, which is a snapshot of the instance at a point of time. Now, if we want to map these different terminologies and concepts to ROS, so topic is going to be the same as a topic in ROS. The domain here will be the ROS ecosystem. The instance will be the message, okay? So an instance here will be the message that is going to bring a data between ROS processes, and the sample, okay, it will be an individual message, okay, that is sent between two processes. So the same terminology was pretty much compatible with the ROS terminology, and I think this is one of the reasons why DDS was adopted for ROS 2 as a middleware for communication. And you have data writer and data reader. So basically here it's pretty much intuitive. Data writer are for publishers, and data reader are for the subscribers. So there is pretty much similarity between the design concept of the data distribution service and also the different concepts for the inter-process communication in ROS, or inter-process communication in ROS. Okay, so DDS finally was chosen. It simplifies a lot the network programming, and it provides inherent publisher-subscriber patterns that are very suitable to ROS, and it shares several similar features with ROS, like topics, creating topics, publishing messages, subscribing to messages, and so on. And it also defines some discovery protocols, because now you don't have a ROS master, so you must have kind of protocol to be able to discover what are the different nodes running in your ecosystem. and it defines messages. So ROS2 messages maintain the same message definition as ROS1, but they need to be converted into a message format that is understood by the DDS transport layer. And this is what we call serialization. Okay, and it has been proven that the serialization is not costly in terms of execution time. And the good thing about DDS, you are not tied to use DDS implementation from one particular vendor. So you can use the DDS implementation from RTI or from OpenSlice DDS or from any other DDS provider. So even in ROS2 now, you can choose which DDS distribution. There are several DDS distributions that are compatible with ROS2 and that you can choose among them. Okay, this is the current state of ROS2. It started from 2017 with the Ardent Apollon, and now in November, November 2019, we have the LSR version. And if you want to start working with ROS2, I would recommend going to this website, which is about the Turtle 3 robot, and they have already provided several simulations and experimentation with ROS2. So they have already enabled ROS2 navigation, and this is native, because in the beginning, usually most of the ROS2 programs were depending on ROS1 programs. They used kind of a bridge. So ROS2, it has only defined the basic commands and the file system, but for example, in the version of Crystal or Bouncy, they did not actually define the navigation stack. The navigation stack started to be defined from Crystal or Dashing, I don't remember well, but now it's already natively implemented into ROS2. Although the current state of ROS2 is still experimental. I mean, it is not as mature as ROS1, but it starts to be more and more mature, and there are already some demonstrations available that you can try out here. So let me finalize my presentation with providing different contributions to ROS. Dr. Ibrahim, do I still have time, maybe 10, 15 minutes? Okay, yes, I will need maybe 10 minutes, yes, to finish. Okay, so we have been using ROS in both education and research. So in terms of education, using ROS was providing as a means to teach ROS for computer science students. And this is not actually very easy, because usually computer scientists, software engineers, as already mentioned in the beginning, they don't have like the sufficient background like electrical engineering and computer engineering about the hardware level. So they want just to focus on the high-level software development. So ROS actually was very perfect framework. This is one application developed by the students for Turtlebot 2 robot, for example, to go to the cafe, bring a coffee, and bring it back to the office here. Okay, this actually allows the students, even from different backgrounds, with software background, software engineering background, to learn about robotics and to develop their own application quite easily. Yes. This is also some other applications that we have developed with the students to emulate a radar system. Okay, to emulate a radar system using a laser rangefinder. And the idea here was actually to detect the speed of a car moving in front of a laser scanner by implementing some kind of speed estimation and making an alarm if the speed was exceeding a certain threshold. So this was done by software engineering and computer science students. It also to introduce students to the world of drones quite easily, because as I mentioned to you now, we would like just, if we want to make the drone move, we want just to send a takeoff command or to send a velocity command, and the robot operating system provides the required, provide different means in order to make these things pretty much simple. This is the AR drone simulator with ROS. Okay, And another thing that we have done also in collaboration with Gaitec company, this is our partner in China. I have been R&D consultant with Gaitec, and we have developed for them this website that is called Gaitec Edu. It contains a lot of tutorials. I have developed a lot of tutorials here. It's a good place to learn about ROS. If you want to learn about navigation or basic concepts, so you can find them here in Turtlebot tutorials. We have also developed a robotic platform that is called the RIA E100. And this platform is designed specifically for research and education. It has a Core i5 computer here. It has a laser of 360 degrees. It has an RGB camera. And you can also extend it with GPUs. You can extend it with robotic arm. It's pretty much complete tool for education and research. And we have a lot of tutorials and resources available that you can find them on edu.gaitec.hk. We have also a bigger platform. This is for research and education. There is another platform that is called the RIA R100, which is bigger in size and for heavier payloads. Okay, another thing that I really enjoy to teach ROS and to share the ROS with others. So I developed different courses on Udemy, ROS for Beginners, Basics, Motion, and OpenCV, and ROS for Beginners 2, which focuses on localization, navigation, and SLAM. I have also another course about ROS 2, the basic concepts of ROS 2, and one other course about programming in Java. So, alhamdulillah, the courses actually are bestsellers now on Udemy. Basically, in terms of content, they were really designed to introduce all the needed concept for robot operating system. And usually I take the benefit from the summer to add more content to my courses. So this course, I developed this one in the previous summer. Now it contains everything related to map-based navigation, but still I need to add some content more to the map-based navigation and also to the reactive navigation. But the current content already provide complete introduction to this, to the important concept for someone, because learning ROS takes time. And there are a lot of ROS courses, a lot of documentation in ROS Wiki, but for someone, a beginner, he's going to be pretty much easily lost into all the different documentation. So here, based on the previous experience of teaching ROS to the students, I have just tried to put all the different resources into one place with live demonstrations. Okay, some of the videos may be old here, but some of the videos are very recent also. This one is a recent course just for the previous summer. For the ROS 2, basically I did this 2 years ago, but it will require that I have to update, because I did this when they have released the bouncy version. And at that time, ROS 2 was not as mature as today. But probably in the summer, I'm going to continue this for making it more comprehensive. But this course just provides an introduction to the new concepts in ROS 2 as compared to ROS 1. Another thing also I have done for the research community is the Springer books. I have now 5 volumes of robot operating system. This series started from 2016. Now we have 5 volumes. The 5th volume is going to be released maybe in 2 or 3 months. And we are accepting chapters for volume number 6. And these books are one of the most downloaded on Springer. So for example, for volume 1, it has been downloaded more than 212,000 times by readers. So if you are interested to submit, I will be glad to receive your submission. You can submit an abstract as soon as you can. And basically the deadline to submit the chapter, it is May 30, but probably due to the COVID-19 issues and stuff like this, maybe I will make an extension for a couple of weeks. Okay, so also I have developed a tutorial a unique tutorial about how to write a global path planner for ROS. And this was one of the most difficult contributions I have done. It was not easy because writing a plugin for ROS is very, very complicated. And at that time, there is no tutorial that tells you how to do this for path planner. So after a lot of search, I have tried to put everything into one place. And now, just by following this tutorial, you will be able to write your own global path planner plugin. For example, if you have a new path planner that maybe outperform A*STAR or Dijkstra, you can try to implement it and test it as a global path planner in ROS. Some other works that we have done is developing service robot with ROS. And here we have tried to develop web services interfaces to be able to communicate a mobile application with ROS. So the idea here is that we have used ROS Java inside the robot to develop web services inside the robot here. And then using a mobile application on Android, we can invoke the web services in Java, and then they will translate these web services request into ROS command to make the robot move and execute a particular action. So here in this demonstration, it was just to make pick and place using a robotic arm and submit the document to another office. So we have developed a complete software abstractions to be able to send the web service request to ROS. I think there is an issue with this slide in particular. Okay, another contribution was also to make multi-robot task allocation, and this is one of the limitations I have talked about ROS, that it doesn't provide any native means to make the robot communicate between each other. Maybe you can do all the robot into one ROS master, but this is not very scalable. So we have developed a complete architecture for multi-robot allocation, which we have called Chorus. And it has different modules. It was built in C++, and it defined a server agent and an operator agent in every robot, and this will allow the robots to exchange messages over a local area network. But you know, at that time, I started to think, why should I be confined to developing application for robots just in a local area network? Because in order to make this robot communicate between each other, I had to work into using one local area network with inside an indoor environment. But my objective was actually to control the robot anywhere and anytime. So there were some strategies for this. Okay, so when we have been doing the experiments, this is the CCIS map that we have built using a robot. Okay, the first floor in our university, and all the experiments were confined to a very limited space. And my objective was to be able to control the robots anywhere and anytime. There were some kind of solutions like using ROS Bridge, but the problem of ROS Bridge is that the server was embedded into the robot itself. ROS Bridge allows you to interact with the robot using web interfaces. And our objective basically is try to move ROS to the cloud. Okay, so and we want to do this for two objectives. The first objective is to make computation offloading instead of processing everything on the robot or on the drone, which have limited, they have limited energy and processing capabilities. We wanted to offload the computation into the cloud, and also we wanted to be able to control these drones or these robots over the cloud using ROS. So we have, this is the problem with ROS. In ROS, usually you have a ROS master, and every robot needs to run its own ROS master, and then you can have one user that is connected to that ROS master. But if you want to control all these robots at once, that was not possible in this way. So another alternative was to use only one ROS master and connect all the robots to it. But this is also not very scalable from one perspective, and you need to make a lot of work in terms of renaming the topics for the different kind of robots. So this solution, although it's feasible, but it's not practical. Okay, if you want to just plug and play any robot to ROS ecosystem and then allow any user to control the robot anywhere and anytime, this solution was not very practical. So at the end, we have designed a cloud-based system, okay, and we developed a serialization protocol that is called the ROS Link that will allow to have a server into the cloud, and then every robot will have its own ROS, okay, with its own ROS master, and here we will define another layer that is called the ROS Link bridge. What it will do, it will serialize the messages from ROS and send them through the cloud. And this will allow several users to connect to the cloud and be connected to their respective robots. Inshallah, in the next lecture after 2 weeks, I will even show you all the details about this solution, and I can show you live demonstrations. I can even give you access to remotely control your robot from wherever you are through the ROS Link cloud system. So this is the ROS Link basic architecture. You have a robot. This is the hardware of the robot, and at the top of it you have ROS. So what we will do, we're going to build the ROS Link bridge, which is another ROS node that will subscribe and publish to all the topics of ROS ecosystem, and then serialize all the messages, send them to a cloud server through the ROS Link proxy. So ROS Link proxy, this is a server here that will receive messages and will forward them to the client. Same thing, the client will have a ROS Link client API that will allow him to receive all the messages about the robots, for example, their states or their locations. And also, he can send commands through all the robots to make them move. He can also receive, now we have also implemented video streaming. We can implement video streaming application from the robot to the end user, and we can send command to the user from up to the robot. Okay, this is one of the first applications that we have implemented to control a drone over the internet. Okay, so this is me here in the football field of Prince Sultan University, and having the following mobile application here. I can send a request to the drone, and the drone is going to follow me, okay, by receiving continuous requests from the mobile application about my position. Okay, and we can even visualize the location of the drone on the Google map in real time. This is another demo based on the same system. Sorry, just remove the volume here. That we have developed for Huawei, and we have tested the system on a 5G network. And basically on 5G, it works pretty much fine in terms of video streaming. We are able to receive video streams. This is through the internet, through the 5G network. And we are able even to locate through 5G the location of the robot while it is navigating in the space. So you can be in any country and your robot in any other country, and you can see in real time where the robot is navigating and what the robot is seeing, okay, through the ROS Link system. Of course, this solution needs a very good communication bandwidth to be able to have a high quality of service. Look here, we can receive up to 20 frames per second from the robot. And this is feasible because we are in 5G network. But in 4G, usually we can reach 4 frames per second, 5 frames per second. Now, the network technology that is used play an important role about the quality of service of the application. So I will finish with this slide. Another work that we have done with ROS also is the platooning. And the platooning here is that we have autonomous cars, one car that autonomously follow another one. This car is driven manually, and this car will try to maintain a safe distance autonomously, okay, using a camera and a laser scanner. So this work was done in collaboration with the Sister Research Center in Portugal, with Enio, our PhD students, and Ricardo Severino also. And we have developed a platooning system. This is also based on ROS, okay, for the demonstration of a platooning system. Okay, so I come to the end of my presentation. So I would say that I will present the technical part about the ROS link in the next lecture after 2 weeks, where I can give more details about how we can make a ROS link bridge and how this enables to control robots and monitor them through the internet. Thank you for following, and I will be pleased to receive your questions.
Thank you very much, Dr. Anis. It's a really exciting and interesting presentation, lots of knowledge today. So please, we will open for a few questions. So I don't know if people can share, can raise their hands here for questions. Anyone has any question, please? He can unmute his mic and ask. Okay, we have one question from...
Hello, Mr. Anis.
Assalamu alaikum. Hello.
I have a question about the hardware.
Yes.
What is the minimal hardware to start using ROS?
Yes, you can use ROS even on a Raspberry Pi. Okay. So, for example, if we take the example of Navio drones, they already use ROS on Raspberry Pi. But the typical hardware is just a computer with Ubuntu operating system if you want to use ROS.
Okay.
Hello.
Yes.
Mr. Anis, hi, good afternoon.
Good afternoon.
I just wanted to understand how the map, indoor map, is appearing on the web browser when it comes to a different network. So I think on the last couple of slides ago, you have mentioned that over the internet, we are able to visualize the map on a browser. So it can be easily possible when we are in the same network, when the robot and our PC.
Yeah.
But how does the indoor map is appearing?
Yeah. This is
the whole.
This is the solution that we have developed. Basically, using the drone map planner, we have developed a system that is called drone map planner. It allows to control and monitor robots and drones over the internet. So when, for example, we want to make robot navigation, what we will do, we are going to send this map is coming from ROS. We will send as an image to the mobile application. So what you see here is a snapshot of the mobile application. Okay? And this mobile application is connected to a 5G network. This robot is connected to 5G networks. So they are completely on separate networks. You can have this application in China, you can have this application in Saudi Arabia, and you still...
But how do we get the localization which is on the robot itself?
Yes.
Usually the localization node is running on the robot, but when we want to show it on a different network on our web browser, even if we have the image of the whole map, it becomes a little difficult to show the real-time position on this map.
Yes. Now, if you have a 5G connection, so ROS is going to find the location at every time, okay, here in ROS.
Okay.
Then we will send this location. This location is going to be taken by the ROS link bridge and will be serialized and sent through the cloud to the end user. So here in the mobile interface of the end user, he can get the location of the robot in real time by taking the location.
But how can we send a position of the robot? It is not a topic that is being published. Because if LiDAR is publishing sensor data, then that topic is published. If any topic is published, that can be shown to a remote browser. We can send that through ROS Bridge or through WebSocket, let us say. But how do we send here?
You will see the implementation in the next week. But let me tell you that in ROS, we have a MCL pose. You know AMCL pose? AMCL pose, that is the pose that is provided by the AMCL package. It gives you the pose of the robot in the map. Now what we will do, this ROS link bridge is going to subscribe to AMCL pose. So every time AMCL pose is going to update the pose of the robot, it will subscribe here. It will take this information, pack it into a message, send it to the cloud, and it will arrive to the ROS link client. And finally, we will be able to visualize it into the mobile interface. Okay, inshallah, in the next demonstration, you will see this live. Okay, and you can do it with your own robot. You can open a simulator robot and plug it into the drone map planner, and you can teleoperate it, and you can see even the location of your robot on the map in real time.
Suppose we develop our own localization packet. Let us say AMCL is also running, but AMCL includes LiDAR plus IMU plus encoder data. But suppose we develop a customized localization node, and that is also publishing a topic which is giving the post with respect to that much data only. So that also can be sent through this?
Yes. Look, the ROS link bridge, any topic that you have here, it will have access to it. Okay, I will show you the way how we have developed ROS link bridge. You can do it for any robot. You can customize it for any robot. What it will do here, basically two things. It will subscribe to any message of interest, and it will publish to any message of interest. Now, when you subscribe to any message, you will forward it to the client to visualize it. And when we publish, so for example, I want to send a velocity command from this robot. For example, I have joystick in this user. It will make any command of joystick. It will be sent to the ROS link bridge, and the ROS link bridge will publish this as a velocity command to ROS to make the robot move.
Of course.
Okay, and this is what you can see here in this demonstration. It's the same thing. Look.
But here you have considered high bandwidth. But for example, there is a low latency network. Then at that point, will there be any offline caching on the robot of that topic that is being subscribed here on the remote browser?
Yeah, we tried this on different networks.
The data should not be lesser?
Yeah, we tried this on different networks, and basically it heavily depends on the network quality. You know, in some cases, like in here in the 5G, it was perfect. I mean, it's like you are running it locally. Now, if you run on 4G, it depends on how much bandwidth you have. If you have any kind of trouble, of course, you will have some latency. You can have some jerking motion. So we are developing this application for the future 5G networks because very soon they are going to be very common. Okay, so
absolutely,
and it will be very easy to deploy this smoothly without any issue.
Thank you so much. Thank you so much.
You're welcome.
Yeah. So any other questions from other? Any other questions?
Thank you, Professor Anis, for your time.
Yes.
Actually, as a beginner, I just wanted to ask that, as you mentioned that ROS2 is prevailing with time and they are developing it. For the beginners, would you recommend to jump into the ROS2 or just start with the ROS?
I would say it's better to have an eye from now, okay? Not to be really behind. Maybe now, if you want to do something very, very advanced, maybe ROS2 is not mature enough, you know. I have also to check the latest distribution, because the latest that I have seen, it was maybe Crystal or that, but I think it is still not as mature as ROS1. This is why most of the ROS users are using just ROS1. But it's important for even a ROS user to be aware about the current development. So whenever ROS2 start to replace ROS1, you have already an introduction and an overview about that. I think it's going to take maybe, let's say, 3 years for ROS2 to completely replace ROS1, based on what I'm seeing as evolution. Yes.
And as you mentioned that there is a problem of like prioritizing the processes in the ROS.
Yes.
And real-time performance.
Yes.
So what do you recommend in those things? Like, it is possible to do multiple processes on real-time at a time?
Look, what was built without QoS, you know, is going to be without QoS. Look, for example, you know, ROS, I would say it's similar to the IP world. You know, IP was designed for best effort, and then they tried to patch it with some kind of quality of service. Okay, it can improve, but it's not inherently built for QoS applications. Okay, same thing for ROS. Now, there are some patches for real-time. I know some people have worked on patches for real-time issues in ROS. Some other people also have worked on ROS security. Okay, one of the chapters in the Springer book of ROS, they have proposed solutions for ROS security. But these are some contributed package. Now, ROS2 was inherently built to be real-time and to inherently support quality of service. Why? Because it uses a middleware that natively support these features. Now, if you look at ROS1, TCP ROS and UDP ROS are just best efforts. So whatever you do, okay, you can improve a little bit the performance, but it's not native performance of quality of service. Okay, and maybe this is one of the limitations why ROS was not maybe, you know, you cannot really rely on it for time-critical applications. Because time-critical application, you need to have guarantees. You need to have to make sure that your message is going to arrive within a certain period of time. And I think ROS2 is going to achieve this sooner or later.
Okay. And as you mentioned that the ROS Kinetis is currently being used by almost 50% of the developers.
Yes.
So for the beginners, like it is one of the basic questions, like which version should I start with? So
For the moment, I just still recommend to use kinetic version. Okay. Although melodic is LTS, but just 2 days ago I heard that someone was having issues of installing OpenCV into the melodic version. So kinetic version was really very stable, and it has all the packages that maybe someone needs for developing advanced applications. Now, if you do something basic at the beginner level, it doesn't matter which version you are going to use, because all of them, they use the same basic concepts. What is the difference is that some packages will spend more time to release some contributed packages than others. Some versions will spend more time to release some packages than the others. For example, you can find some packages that are mature in kinetic, but still not in melodic. So you will have to wait a little bit until melodic will release these packages. You see what I mean?
yeah.
But if you do at the basic level, it doesn't matter anyone you will use. Okay. Now in my ROS course, I recommended to use kinetic because I know that some of the packages, at least at that time, were not available in melodic.
Okay.
Yeah.
And one more thing, like as you know, there are multiple robots like Pepper Robot and Neo Robot. So do you have any plan to like make a course or on the ROS and the NeoKey SDK like that?
Yeah, no, my plan is actually to improve the ROS navigation course, because I have to add some part about reactive navigation. For example, how to implement a navigation without a map using the bug algorithm and some common techniques. And I will also develop some courses related to deep learning, and also some courses about how to integrate deep learning with ROS. These are my future plans, at least for maybe this summer.
Like I wanted to ask about the how to use ROS with Neo Robot or Pepper Robot.
Yeah, these are humanoid robot. Honestly, I didn't work with them a lot because I was focusing more on aerial and ground robots.
Okay.
Yes.
Thank you.
You're welcome.
Thank you for your time.
You're welcome.
So it's the same question with Hamad also. It's about interaction. If we need to build some services to interact with patients in area of social robots, is it really possible in the near future to have something ready for people to use?
For the social robots?
Yes.
Look, I mean, if you use ROS, for me, when I use ROS, it doesn't matter what kind of robot it is, whether it is humanoid or it is something. Okay, because what you are going to interact with topics, and these topics either will be coming from sensors, so the sensor can be from a humanoid robot in his eyes, or from just the camera from the ground robot, and then you will publish velocity comments. So the good thing in ROS that it will make abstraction, so you can reuse some existing ideas from aerial robotics or ground robotics, and you can maybe implement them into humanoid robots. But for humanoid, basically, I didn't work on them so far.
Yeah. We have a question from Muhammad Khalil.
Yes?
Yeah.
Are you ready about the hardware?
Sorry?
Are you ready asked my question about the hardware?
Okay.
Hello.
Hello? Yes.
Yeah. First off, thank you for the very informative lecture. I have followed your 2 courses of ROS on Udemy, and they have been very helpful in me working on ROS. One thing that I would like to ask you is when developing a robot from scratch, as also Khalil asked, one thing that I see is missing in many tutorials is that the TF module and setting up proper transforms on a robot with odometry and encoders and lidars. Is there like a comprehensive tutorial or course on that regard?
Yeah, I see the question, yes. Basically, this has to do with defining the URDF model of the robot, right? There are some nice tutorials on the book that is called ROS by Examples. I really like this series. Okay, although it was developed until the ROS and Digo version, but still the same concept can be used. So I would recommend that you go to ROS by Examples, Volume 2, and they have very nice tutorials on how to build a robot from scratch. But you know, building a robot from scratch in ROS, this means that you need to define the URDF model of the robot. This is an interesting area. It's probable that I can make a chapter on my course that is on robot localization, because in this course I have already introduced the concept of URDF, but I didn't talk into details about how to build a robot from scratch. But this could be a good extension to the course. I will try to take this into account.
Yeah, that would be very helpful, because most courses use the simulation or the turtle robots.
Yes.
If we can see an instructor teaching us on a robot from scratch and building the URDF in a course, that would, I think, help a lot of people like me. Once again, thank you, sir.
Thank you, yes. But also I would recommend that if you are in a hurry, you can look at the ROS by Examples book. It is very nice and provides step by step.
I will.
Yes.
Hello.
Yes.
Anish, wanted to ask you about the 3-wheel machine. So everywhere, everybody is experimenting on 2 wheels. So there are some machines which are 3-wheel, but in 3-wheel it is very indifferent, where the front wheel only has the drive motor as well as the steering motor both. So the front one is having both one, and the backside 2 are just rolling.
Yes.
So in that case, a typical ROS library does not work, where there is a precondition where all the 3 wheels would have motor.
Yes. Now, this is related to writing drivers for your motors, and writing the drivers is something not easy, because you need to develop the low-level drivers for every motor, how they should work, and this depends whether they are differential motors or Ackermann steering motors. Okay.
No, so it is the problem with the Ackermann, actually, not with the motor, but what happens is on the front tire, where there is 1 wheel, on the back side there are 2 wheels. On the front wheel it is having a driving motor as well as a steering motor both.
Yes.
But in both those motors there will be encoder attached, so we don't get the exact encoder topic published which will give the position properly. So there is no proper ROS package which can show the robot position with respect to this kind of a configuration, where front one is having both the drive and steer.
This is your own robot. You have developed your own robot.
Yes.
So in this case, you have to look how the drivers has been written, because now, for example, even when we have developed the robot, this one that you see here, writing the driver was something very complex, and it has to be done by someone specialized in this. Because there are a lot of dynamic equations that have to be considered when you write the code for the low-level drivers, for them to work properly. Otherwise, the information that you will get from the encoders will not be correct, and in this case, it will not help in the localization, and it will not help in performing the navigation. Okay.
Yeah, that is why, because the whole navigation stack will not work if the base thing is not proper.
Yes, but if you buy a robot, you just need to make sure that the robot supports ROS. Because for me, I don't care about writing low-level drivers. I just need to take the robot as just providing the information about the odometry and the information about the how to publish.
Can you suggest any project or book where it has been given a similar example with this kind of thing? Just like the earlier question with somebody else, you mentioned that ROS by Examples Volume 2 has that particular, building the robot from scratch.
Look, you can.
But can you give particularly for 3-wheel configuration of this? If you can.
You can contact me by email, and I will try to put you in contact with some people
Definitely.
that I know that they have developed these kind of things.
Definitely. Thank you so much.
Yeah. Okay. Any other question?
Any other question from? I guess we don't have more questions.
Okay.
So we will meet again in 2 weeks.
Excuse me, I have one more question, if I may ask.
Yes.
So Anish, there is one more question regarding serial issue. So typically when we are using Raspberry Pi as the main ROS master, and then if we use an Arduino, for getting the data of, let us say, IMU or something, then always there is a ROS serial kind of a issue comes, which is not just for loose connection or something, but with the Arduino there will be some or the other ROS serial issue that will come. When we use TinZ board is also, there's an ARM board now very famous right now. So with that use, that does not come. And sometimes processor also hangs, so we are not sure whether we use Ubiquiti or Dustbuster and this particular board. So the ROS serial issue is abruptly coming at any time. It doesn't know what is the exact reason.
Yeah, we have been using ROS serial for like simple application with ultrasonic sensors. But now, if you are having issues, it might be related to the baud rate. Okay, you need to check about the baud rate. Maybe if you have the baud rate higher than what the serial connection can support, you can have this kind of hanging and problems.
Okay.
Yeah.
Sometimes it is losing the sync. Of course, it might be a baud rate issue, but sometimes it is properly running for 1-2 hours. Then after 1-2 hours, it will create a problem.
Yeah, and maybe you need also, sometimes you need to flush the buffers. Maybe there is buffering overflow. There is different kind of reasons. It depends on how how this was implemented. For the application that we have used, ROS serial, we didn't face these kind of issues. But if you are facing, maybe this is related to buffer overflow or baud rate issues or stuff like this. So it's basically low-level hardware issue. You can check your C drivers that you have made. Is it the typical ROS serial Arduino provided by ROS, or it's another package?
Yes, it is the normal Arduino that we use.
Yeah. Yeah, it depends. Try to check the baud rate. This is the first thing I will look at. Try to check the frequency of how much data you are sending per second. Maybe you try to reduce it a little bit if it's possible. Okay, and check again.
Sure, definitely.
Yeah.
I'll check.
Yes.
Yeah. Thank you very much, Dr. Anis, for today.
Thank you.
It was very educative today, and we're really excited for the next meeting after 2 weeks.
Inshallah, thank you.
So please, people, today, just to prepare your questions for next time, and please join us next time. We will announce the event for the next time after 2 weeks very soon.
Okay, thank you. Thank you for the invitation, Dr. Ibrahim. It was my pleasure to provide you the presentation.
Thank you very much, Dr. Anis.
Okay,
thank you very much for everyone. And
Thank you so much.
Thank you.
Thank you very much.
Thank you.
See you next time.
Bye.
Bye-bye.
Bye.